in Europe. And as I told you, this is the second European Fire Safety Week. Last year in 2019, we had the first one, and that was very necessary because we really needed to have more awareness on fire safety. And as you know, a lot of people talk about fire safety, but sometimes you need a disaster to keep people focused on what's really about. And ladies and gentlemen, we really have to realize that we have more than 5,000 casualties every year in Europe. That's about 2 Grenfell disasters a week about fire safety. So the European Fire Safety Week was about awareness, was about connecting specialists, was about learning from each other, but last but not least, making things work. And that's what this European Fire Safety Week is also all about, making things work. And last year we made the conclusions, we put the conclusions together and we made, yes, we made just
Ulf, could you perhaps mute your microphone? I think
the
noise is coming from. Sorry.
So I hope you can hear me, and I will continue. The results of the European Fire Safety Week from last year were collected, and we had our first agenda for the coming years. And the European Fire Safety Action Plan we have now is what, as far as I'm concerned, the action and the agenda for the coming 2 years. It's about the action on growing vulnerability. It's about the reduction of escape time, which is very scary. It's about energy transition, where we talk about today. It's about awareness. It's about data collecting, because do we know what we talk about? And it's about collaboration and communication. And all those issues are extremely important points of the European Fire Safety Action Plan we are talking about now. And this week, in the second European Fire Safety Week, we are really going to talk about the progress on those issues. We are together with more than 500 people from 40 countries. So, well, ladies and gentlemen, we really can make the difference, I hope, in those coming days. And today we are talking about a very interesting and important issue, and that's energy transition. And this morning we talk about energy transition in transport. And we will hear a lot of interesting things. And I appreciate very much the hard work of the PINFA to make this come true, this excellent webinar. And we're really looking forward to speakers. And I'm glad to introduce the chair of the PINFA, Mr. Adrian Beard.
Thanks very much, Eli, for the kind introduction and your introductory words. Also, a warm welcome to me, ladies and gentlemen, this morning. My name is Adrian Beard. I am the chairman of PINFA, the Association for Phosphorus, Inorganic and Nitrogen Flame Retardants. I also work for Clariant, a Swiss-based specialty chemicals company, but I'm based near Cologne in Germany. My background is in environmental sciences, but I've been working in the field of flame retardants for more than 20 years now. If we go to the next page, you'll have a preview of the agenda for today, the program. We have 2 blocks. At 10:10 in a few minutes, we will start with the first block on fire risks of road vehicles and how these risks are changing with electric vehicles. And in the second block, we will speak about specific risks of e-vehicles charging and parking in buildings. And after each block, there's the opportunity to ask questions and then have a short discussion. Going to the next page, who is PINFA? As I said, the Phosphorus, Inorganic and Nitrogen Flame Retardants Association was established in 2009 as a sector group of CEFIC, the European Chemical Industry Council. And we also have sister associations in North America and China set up in the meantime. And on the next page, just a quick snapshot of our membership. So you'll see big familiar names from the chemical industry, but also smaller specialized companies. And PINFA brings together not only producers of flame retardants, but also downstream users of flame retardants, because we want to collaborate along the value chain. Going to the next slide, just also a quick view on our leadership team within pinfa. So there is Esther and Hanan, based at Cefic in Brussels, who take care of our daily operations. And I have two vice chairmen, Michael Klimes and Thomas Futterer. Now let's I'll finally have a look at social media. So where do you find more information about us? The web, of course, pinfa.org or pinfa.eu. We also have a LinkedIn account and, of course, Twitter account these days. All right, then let's jump into today's meeting. But before we go to the talks, some brief words on housekeeping. So on the next slide, please mute your microphone. And we just saw the example of the disturbing noise coming in. So if everyone who's not speaking, please mute the microphone, that really helps. Because we're such a large group, we already have around about 100 attendees. Please use the raise your hand function in Microsoft Teams to alert us that you want to ask a question, but you also can use the chat function. And as said, we'll have 3 short presentations and after them time for Q&A. And we're not allowed, and this you see here on this slide, do's and don'ts. Certain things we're not allowed to do in this call because it involves industry participants also from competing companies. So we have to strictly adhere to competition law, antitrust law. And so we must not speak about pricing, about customers, about market segmentation, and so forth. And we must, on the left-hand side here, be vigilant that we observe all these rules. And that's also why we have Cefic people here on board who also make sure that we don't violate these rules. But I'm sure today's topic is not sensitive in that, or shouldn't be sensitive in that respect. Okay, with that, we come to the meat of or the heart of this morning's webinar. Let me just briefly introduce the speakers to you on the following pages. So we have Paul Ochuterena. He's a senior researcher at the Division of Safety and Transport at RISE in Sweden, and his field of research involves combustion, aerosols, and optics. And on the next page, we see Professor Ulf Björnstig from the University of Umeå. He's a general surgeon and focuses on pediatric surgery, and also has experience and great interest in traffic and vehicle-related injuries, and that's also why he will be speaking to us today. Go to the next speaker is David Key from Radici. He's a polymer engineer and has worked for various big polymer companies, Polyone, Celanese, you see here, and is now with Radici, and in the area of polymers for transport applications like electromobility. And on the next page, Vincent Muntz. He's our consultant within pinfa, technical consultant. He has more than 30 years experience in flame retardants and passive fire protection. He has been active as a member on various standardization committees, and he also used to be the president of the European for Passive Fire Protection. And then we have Laurent Tribu, a polymer expert who works at Schneider, but has also a history working for other companies like Lexans, experience so in wire and cables, a lot of experience in flame retardant formulations, also work in standardization bodies like IEC, and he's also a member of our pinfa advisory board. And then further, Dieter Brands, a colleague from the fire services. He graduated from the University of Leuven and now works with the fire brigade and is very active in fire safety activities in Belgium. And he will be speaking later to us from the fire station, as we saw earlier. So looking very much forward to that. And then we have Lars Derek Mellet from Switzerland joining us. He works for a consulting company, Walter Progress AG, and has interest or is an expert in tunnel fire safety. So applied research projects on road tunnel safety and operational safety equipment in these tunnels, and we'll hear from him later on the specific issues that these tunnels pose for safety involving electric vehicles. Yes, with that we come to the first presentation, and that will be Paul, and he'll speak about fire risks of road vehicles and how these risks are changing with vehicle safety.
Hi, my name is Paul Drake, and this work was done together with Ulf Björnstig and Mats Lindqvist. You will hear Ulf talking about more about the medicine part of emissions from fire in 7 or 8 minutes. Could you please put next slide? I'm going to talk mostly about post-crash fires in road vehicles, and the main part of this is, well, how important it is. Oh, now it disappears. We consider that 5% of all fatalities in the Swedish roads between 1998 and 2008, that means a 10-year-old period, occurred in burning vehicles. And then we consider that we extrapolate that, or we just change to another continent, to American continent, and we take United States. We see that 31 vehicles fire are reported each hour, and they are responsible for 300 deaths and 800 persons injured per year. And the problem of this is that the cause of death in 1/3 of the reported incident is just attributable to fire. And as well, that means that the fire are involved in 12% of the fire deaths, and 8% of the civilian fire injuries, and 9% of direct property. And if we take a look on the chart that is at your left-hand side, then we see that between 2002 and 2014, we have an amount of total vehicles that are involved, and this is apparently the amount of vehicles that are catching fire is being reduced from 58,000 to 44,000, which is very good. On the other hand, if we consider in the third column that the vehicles catching fire, that's increased from 2.95% to 3.28%. Well, it's just 0.5%, right? It doesn't seem to be a lot. But if we consider about the casualties in traffic, and we take the last column, then we see that fatalities occurring in vehicle catching fires goes from 4.55% to 5.36% in this 12-year period. That means that increase is just the amount of persons who die due to fire is increasing. So if you please take the next slide. Then if we just take a look at about the primary factor involved in ignition and fire rate, and this is according to the age of vehicles, then we see that, well, modern vehicles, they have just a slightly increase in catching fire, at least as it's going with 2014. That means not just all the vehicles, but that means the modern vehicles, they have a slightly increase from 2.5% to 3.5%. If we talk about the primary factor involved in ignition, oh, there is some microphone here. But
yeah. Can everybody please mute? I'm gonna mute all, and Paul, if you can unmute yourself to take care of this
yes.
issue. Okay, I'm gonna hit mute all, and then. Okay, so Paul, if you can unmute yourself now, and then we can continue.
Super, thank you. If we consider that the mechanical failure and malfunction, this is quite important. That leads to almost 10% of the vehicles. But there is something interesting in the third row, that is a misuse of material product. That means that it's a poor engineering judgment. That's the person that chooses the part of that material that should be used in the vehicle. It was not the proper one. And there are other factors like collision, that is, well, 3.6%, and other insulation or natural condition. I mean, that probably the vehicle got fired because of something else. Could you please take this next slide? I'm talking just about fires in vehicles due to a collision in this part, and thus we're now showing the initial point of impact and origin of minor and major fire. And there is a chart at your left-hand side, which shows that, in principle, what is the most important for a collision, or the most representative, overrepresented type of collision, is a frontal collision. And then we take, in the right-hand side, there is a chart which shows the occurrence, origin, and then there is the two right columns that is unweighted and weighted. I mean, because we take a look at the statistics, and then when we weight it, that means how many fires it will correspond in statistics for the United States. And we see that most of the fires, indeed, they commence in the engine compartment as a minor occurrence. As a major occurrence, it occurs the same. And you continue to the next one, please. And then we take the area of origin and cause of fire, and that's probably the most important part. How you translate the statistics that I just showed you. And we take about the engine area, the running gear, and the wheel area. They are probably the most important part for major vehicles in transport. But as well, we consider fatalities that are the red color, the orange or red, however, whichever color you see. It's as well overrepresented, and that's, I mean, the 80%, or almost 80% of the major vehicle incidents, it commences in the engine area, and almost 40% of the fatalities occur due to fires that originate in the engine area. If we think about this, just to the right-hand side chart, which is similar, but it's about the cause of fire. Then the cause of fire is due to operational deficiency or collision. That there's most of the fatalities, but not most of the fire. That means that operational deficiency or collision leads to the major amount of fatalities, even though it's not the overrepresented, because mechanical failure and malfunction is the one that occurs the major vehicle incident fire. But fatalities, collisions, is the one that leads to major deaths due to just fire, or event that is just attributable to fire. Could you show the next, please? And then if we consider the amount of energy that is dissipated in each crash, and if we take about the amount of fatalities that lead to this, it's not surprising that increasing the energy of a fire, increasing the energy of a collision will lead to a higher probability of catching a fire. And I would like to say that when we arrive to more to 2,000 megajoule, 2 megajoule is a massive amount of energy that is dissipating on a crash. This is most of the crashes, that's the 3% are in this region, about 2 megajoules. But when we arrive to 4 megajoules, then the probability of catching a fire and die in a collision is massive. But part of the sad part of it is that we have improved a lot the survivability of crashing in vehicles, but the fire is the probability of catching a fire is larger. That means that we have a better probability of surviving a crash due to traumatic injuries, but we have a lower probability of surviving the crash of a vehicle due that the vehicle is going to catch a fire. And then the next one, please. And then what happens when we compare, this is without having a crashing comparison, but what happens when we compare internal combustion engines with electrical vehicles? So we have we did some measurements and some studies in the literature. And in the left side, there is a chart when we are measuring carbon dioxide, carbon monoxide, hydrocarbons, nitrogen monoxide, nitrogen dioxide, fluoridic acid, and cyanides. We compare just the amount of electrical vehicles and internal combustion engines. Of course, we see that in front of all, the hydrogen fluoride is much higher for the production of hydrogen fluoride and chloride is much higher for electrical vehicles than for internal combustion engine vehicles. And this is, of course, not surprising since we have been expecting it. Then there is a chart when we compare the amount of energy of the battery against the hydrogen fluoride that is produced. And as you can see, of course, the larger the battery, the larger amount of hydrogen fluoride that is produced. And there is some amount of tests that are being produced in ETOX, that is in our one project from RISE, and there is as well from INERIS, that is just from vehicle tests on the battery, that is a larger scale test. And then my last slide, so if you would like to have further information, the next, there is an article produced by Mats Lindqvist, Ulf, Björnstig, and me that you are welcome to read, or I can send it the PDF to you if you contact me. Well, that was it. Thanks.
Thanks very much, Paul. And then we hand over directly to Ulf.
Thank you. Can we take the first slide? Thank you. Fires in cars are often serious incidents. However, competent medical treatment of the effect of fire emissions may save some lives. I would say, as Barack Obama said, there is hope. Second slide, please. Our results are presented in Traffic Injury Prevention 2013, and I would point out some important parts of that. Next slide, please. 5 to 8% of those who died in a passenger car in Sweden during these 11 years died in a burning car. In total, it was 181 victims. These crashes were high-energy crashes. Consequently, 2/3 had also other fatal injuries than burns. However, 55 victims had no other fatal injuries, and they should probably have been alive today, if not a fire had developed. A majority of these were passengers, often in the rear seat, where we used to have our children. Next slide. We have recently repeated this study. Interesting is that the forensic pathologists have identified hydrogen cyanide in at least 10 victims of 18 dying because of the fire. I will talk more about this substance later. Next, please. Does e-vehicles cause new problems with respect on gas emissions? Paul pointed out one substance. Maybe it will be so. We'll wait and see. Next picture, yeah. The smoke may have three main effects, as you see on this slide. Next slide. First, we have the oxygenation problem. Three factors that are additive and contribute to compromising the oxygenation of cells are, for the first, lack of oxygen in the air. If the level is below 10%, it is too low. This may happen in a closed space, for example, in a ferry, in an underground garage, when the fire has consumed the oxygen from the air. The second factor is carbon monoxide, and the third is hydrogen cyanide, both with very important effects, but possible to handle. Next slide, please. Carbon monoxide attached 250 times easier than oxygen to the hemoglobin in the red blood cells, thus blocking the uptake of oxygen. High level of carbon monoxide cause death, but quick and competent treatment may save some victims. A pitfall is a fresh red color of carbon monoxide hemoglobin in intoxicated victims. That could be misinterpreted. Yeah, next slide. The third oxygen compromising factor is cyanide, which is a highly toxic gas causing death quickly in low concentrations. The cyanide ion goes easy from the bloodstream into the cell, and in the cell it shuts off the energy production in that cell. Consequently, the cell cannot absorb any oxygen from the bloodstream. Next, please. Cyanide smells bitter almond, causes confusion, convulsions, and finally death. Next, please. Does a vehicle add more to these problems? Yes, maybe. A burning traction battery produces often hydrogen fluoride, HF. However, HF may also be produced by, for example, the air-conditioned liquid burning also in other cars. I don't know, but a recent rumor indicates that eventually may the same liquid be used in e-vehicles' traction battery cooling system. I do not know, but if this is true, it would be bad. Next slide. HF has two major physical effects. The first is a corrosive effect causing swelling and bleeding in the airways that may cause severe respiration problems. Next, please. The second effect is changes in the electrolyte balance in blood, of which a low calcium level may cause heart arrhythmias, and a high potassium level will cause severe muscular pain. Next, please. So how to treat the victim? First, always oxygen, preferably 100% under overpressure if possible. Second, if edema and swelling in the airways, put an endotracheal tube into the upper airway to secure the breathing. 3, asthma drugs against bronchus widening drug plus cortisone drug against swelling. Next slide, please. The fourth point is, if the victim has impaired consciousness, give an antidote against cyanide, in this case cyanokit, a fantastic safe drug, reversing the block of energy-producing mitochondria in the cell. However, the drug is a little expensive, so not all ambulance organizations use it. Next, please. How to handle HF-impaired victims. If heart arrhythmia, they need calcium. If the victim is conscious, possible to give him or her calcium tablets via the mouth. These victims may quickly deteriorate, so they should be taken to hospital. And in severe cases, they may need intensive care or pressure chamber if available. Next. Thank you from two hopefully fluoride-free veterans. That was the end.
Thanks very much, Ulf. Thank you. And a nice car, by the way.
Yeah, 50 years.
Very nice.
No fluoride in that car.
Good, we come to the next presentation. David is up next. David Key from Radici, and he's sharing his screen himself. That was the plan.
Yep. Andrew, can you see me? See my screen right now?
It's coming. Yeah, it's yet.
Maybe I should hide this one. Sorry. Okay, can you see my screen?
I still have a black screen, but yeah. Esther, do you see it? I only have a black screen.
Not yet.
Sorry.
Okay.
I'm gonna share this one. Can you see my screen right now?
No.
Not yet.
No.
No.
You click in the box with the down arrow.
Yes, and I shared my presentation.
Okay. So then
You still cannot see that?
No, it might be a network issue, but
Oh, well, we see the video fine, so.
So maybe say you have my presentation. Maybe you can
share it.
share.
Yeah.
Yeah.
Maybe
Yeah,
yes, you
thank
pull
you.
it up, yeah. Yes, sorry guys, it worked the last time perfectly with David, so it's so that's why we were very confident it would work again today. But it's here it comes, yeah.
Okay, so maybe
Right.
next, please, and next. Okay, so good morning, everyone. I'm David Key from Rentici Plastics, China. I'm responsible for the business development and also the CAE validation and also optimization. So next page, please. Okay, so here's the content of my presentation. I'm going to briefly introduce you about the Rentici Group and then our integrated solutions in the new energy vehicles and also the challenges that we are facing in currently and also in the future. Next, please. Okay, and next. Okay, here's the histories of the Rentici Group. The group is founded in 1920. And in 1960 and 1980, we started our own implementation of both PSX and PSXX. And in 2011, we started the implementation of the long-chain polyamide, which including the PSX10, PSX12. And in 2013, we launched the new high temperatures nylon, which can survive the temperatures up to 190 degrees Celsius and also 230 degrees Celsius, only for the, let's say, integrated engine components. And in 2016, we launched the new high stiffness polyamide, and we also targeted on the battery pack segment with this new high stiffness polyamides. Next, please. Here's our global site. We are a global corporate for support all the areas customers need. Next, please. And here's the our product portfolio. So basically, we are polyamide upstream integrated solution suppliers, and also besides that, we also provide customers with one-stop solutions, including other materials like PPS, PPT, POM, and etc. Yeah, next, and next, please. Okay. So here's the first summary I would like to share with everyone about the challenge we are facing right now, and also maybe also be the challenge for the future. On the very left side, you can see these parts we are supplying to our customers for the new energy vehicles. But at the very beginning, you can see these materials for the flame retardant. It appears with the contact corrosions issues. And this also will cause the electric breakdown issues, which might cause the fire on the field. So after that, we supply the customers with non-contact corrosions solutions materials to solve this problem. And also, this is for the new energy vehicles. But if you think about the fuel cell vehicles on the fuel stack areas, right now, it's very hard to use the flame retardant materials because these areas, they need to be very careful for the materials content, including the metal irons or the halides irons. So right now, it's a little bit hard for the flame retardant materials to be used for the fuel cell stocks. And the yellow, the orange colors is also a problem right now. Because the initial colors will be RAL 2003. You can see it's very light, bright orange colors. But after a little bit heat agings, the colors will be a little bit dark. And this is could be causing some issues. And customers asking us to have a very constant color performance. And besides that, during the plastics component tested in the new energy vehicles, we have also seen several other issues with the materials volume resistant. As you can see that for plastics, their initial volume resistance is at very high level, which is really good to be isolated materials. But after different temperatures, heat agings, you can see this volume resistance has been rapidly dropped to very low levels. This could cause the electrical breakdown, which can cause the fire issues. For that, we are cooperating with our R&D centers, and also the customers try to solve this problem. And also for the dielectric strengths, as you can see, for different temperatures, these dielectric strengths will be dropped rapidly as well. For this, we have worked with our customers for the ground wireless charging systems, and these properties could significantly impact the whole component survival on the high temperatures, and would cause the electrical breakdowns. Okay, next, please. Next, please. Okay. Yeah. Okay. So here you can see this is the future challenge. As you can see in the middle, there's the high power charging systems, which means that the charging voltage will be the traditional 220 volts to 1000 volts. So for these areas, the materials need to be flame retardant, but meanwhile, these materials need to have very low volume resistant, because the voltage is at very high level. You need to avoid the electron charge accumulation, which we call the anti-static performance. And besides that, for the very right one, the EV wireless chargings, you can see these new global standards. The first one, GB, is the China national standards, which is issued just last month. And in Europe, the SAEJ standards has been issued this May, which also requires very low volume and service resistant. And meanwhile, you need to have very good dielectric strength. And this is also very challenging for the flame retardant materials. Next, please. Okay, so as you can see here, for the battery pack now in China, we just issued the new regulations, which is the mandatory regulations now, GB 38031. So for this, it's going to replace the old recommended regulations, which is GB/T 31467, and also GB/T 31485. And for the big changes that, as you can see on within these regulations, there are over 14 items tested for the battery pack. But among these, there are two test items which is really important. The first one is the fire test, as you can see on the very right bottom. For the new regulations now, this battery would be put onto the fire for 70 seconds. For the new, for the old regulations, it says that when the fire is moved away, this battery pack could catch fire, but this fire should be self-extinguished within 2 minutes. But now the new regulations remove the self-extinguish within 2 minutes request, but keep the fire test and without any explosion. And the new regulations also focused very careful on the, let's say, the thermal runaway. So they update the vibration test, which is the first one on the left, the upper left. So in the older regulations, it's only requested the signal regulations test, but now is requested the PSD, random vibrations, combined with the thermal temperatures, which could be very challenging for the materials. Next, please. Okay, here is a short video we tested for our customers for the 48 battery pack. As you can see, the whole test. And now we are helping customers to launch the PA6 filled with 30% glass fiber V0 grade to survive on this fail test. Next, please. Okay, so next I'm going to show you very interesting the materials trend used for the new energy vehicles. Next. Here is the core work we had with Renault back to 2011. As you can see, here is the material boom for only the powertrain systems. Very interesting thing is that you can see that for the hybrid vehicles, which is the 1.5 turbulence engine PHEV vehicles, there's very interesting the material trend, as you can see here, for the PS6s and also PBT. The usage for the new energy vehicles has been almost tripled compared with the traditional ICE engines like the 1.5T turbulence engine, diesel, and also the 1.6 turbulence engines, gasoline engines. So this is the very interesting trend. Next, thank you. Okay, so as everyone knows that for the new energy vehicles, there are three core technology: e-motor, battery, and electrical controls. And I'm going to show you several typical applications. Next, please. Here you can see the e-control systems, which including the PDU, power distribution unit, and PCU, power control unit. And those are metal, but if you open it up, you can see a lot of plastics components within them. Next, please. Yes, so now you can see the PDU if you open it up. Next, and next. Okay, so you can see a lot of plastics parts within these PDU housings, or you can call it junction box. Next. Yes, and next. Okay, so you can see here there's a lot of parts here for the junction box, and also for the battery pack. You can see here for battery modules, we have several grades for the battery module brackets, which is using PA66 filled with 50% glass fiber, V0 grade, and also for the battery management systems, also use the PA66 V0 grade, and also the battery frame, PA66 filled with 25% glass fiber V0 grade. But for all of these components, we should be very careful with the corrosion, the contact corrosion issues, and also the volume resistant drops, which can cause the electrical breakdown, which will finally cause the fire on the field. Okay, thank you. Okay, thank you.
Thanks very much, David.
Thank you.
Very good. Yes, so now we have a short Q&A session or time for some questions. There was one question in the chat that I saw earlier. Will the presentations be shared? Yes, that's our plan. We will share them. Also, the recording of this session will also be made available. So to just answer that. Ulf, you raised your hand.
Sorry, that was a mistake.
Okay.
I should look at the chat.
Okay, so any questions, please raise your hand, or I'm also going to have a look at the chat if there's anything. There were some technical issues being discussed in the chat. I hope
yeah, just a short question, please. Frank Puig from Crepim. One of the speakers spoken about fluorhydric acid. Is that any possibility to add a scavenger in order to trap the acid during release during the fire?
Maybe I can comment on that. Perhaps others can as well. So the hydrofluoric acid that is released from batteries is due to the in addition to the electrolyte that is lithium phosphorus hexafluoride. Yeah. So it's in the battery, and it's not related to cooling fluids chemically. So it's something else. If in the battery you could add a scavenger, I don't know. I haven't heard of it. David, have you perhaps heard of anything like that?
Sorry,
David, you're on mute. Yeah, if you unmute.
Pardon me. What is the question? Sorry.
No, the question was if the fluoride HF released from batteries, that is possible in a fire situation. Have you heard of adding acid scavengers to the battery enclosure or somewhere as a countermeasure? Yeah.
Actually, right now for the new China regulations, they asked to put a lot of sensors inside of the battery pack to test the, for example, the temperatures and also the moistures. And if you think about the fuel cell vehicles, yes, they have a lot of the sensors to test the hydrogen, because as you know, the hydrogen is a gas which is hardly to be detected by the eyeballs. And when it catch fire, actually the hydrogen fire is you cannot see the fire, actually, not like other fires. So it's very hard when the hydrogens leak and catches fire. It's very hard to be detected or observed. So that is why for this kind of vehicles, there are quite a lot of sensors to test the hydrogens.
Okay. Okay, so that's yet another topic. Maybe there's one question, David, also to you from Chris Lesak here. I see you mentioned the Chinese battery fire test. Is there an equivalent European test for these kind of batteries?
Yes, I think it is IEC 100 or 110.
Mm-hmm.
Yeah, it's very equivalent.
Okay, very similar. Okay.
Yeah.
Thanks.
We have a hand raised, Adrian.
Okay. So I was just looking at the chat. So
hi, hello.
Yes, go ahead.
Hi, hello. It's David from Malta.
Okay.
My question is electric vehicles in general. We have been noticing that manufacturers are installing the safety fuse. However, there is no European confirmation or standard which says, listen, all these safety fuses have to be in this specific location.
Mm-hmm.
We are seeing different manufacturers who are installing this fuse in different parts of the vehicle, and the same manufacturer is having the safety fuse in different parts depending on the model. If we take an example of a car, we have manufacturer A, which has the safety fuse in the front compartment. In a different model, it's in the passenger compartment, and in a different model, it's behind the rear seat of the passenger compartment. So can there be a globalization and a standard for this specific fuse? Because as firefighters, when we are going on an incident, this is causing quite an issue sometimes.
Yes,
No,
this is really, Andrew, go on.
No, okay, go ahead, David.
Okay, so this is a really good question. Actually, for the China new regulations, GB 38031, they put a lot of, let's say, the thermal runaway test into these new regulations. And for the thermal runaway test, they require a test at different SOC levels. For example, 25%, 50%, 100%, and even higher. And for those, it requires the OEMs to put a lot of, like the fuel box, but now we call it the relay box into these batteries. Actually, for the junction box, they have put a lot of junction boxes to control the currents, which goes in and out of the batteries. And for this part, maybe you cannot see before you open the batteries, but there's one battery might interest you. That is the battery from Tesla. For the Tesla battery, if you open up, you can see a lot of pins on each secondary batteries. And those pins is actually the fuse to keep the single secondary battery safe.
Okay, thanks for that comment. I think in view of time, we have to move on. Sorry for questions we cannot further take, but I suggest we move on because we're slightly behind time. But I also want to give sufficient time for the next speakers for their presentations. So with that, I'd like to hand over to Vincent to speak to us about the implications. So far, we were speaking of vehicles on the road, and now we look at what about stationary vehicles and garages, because garages may be becoming fuel stations in the end if you have a battery of or lineup of charging stations there. Over to you, Vincent. Vincent, do you need to unmute? Where is?
Sorry for that.
Yep.
Thanks, Adrian. Good morning to everyone. What I'm going to present here is an overview of the impact of electric vehicles regarding fire safety in garages as an introduction for this second block in this webinar. Next. Well, e-vehicles are on the move, this is clear. The newspapers talks about that. And basically because there is a fast growth due to green political objectives like the horizon for the carbon. And in particular because a progressive understanding of the global warming by the society, and therefore the consequent demand on green products. Next. If we have a look on the fire occurrence in electric vehicles, recent studies in 2018 and 2019 showed that about 50% of the fires in electric vehicles happen in cars when they were parked or being charged or just being charged. Next, please. If we have a look, what will happen in future? So we have plenty of big garages with a long and wide batteries of chargers, and this really represent a risk in such things in a closed space. Next. If we revise a little bit the actual regulation intended for ICE vehicles, so internal combustion engines, normal vehicles, which is a regulation which is up to member states right now in the European Union, but framed within the European Construction Codes, so-called Eurocodes. And basically is requires for garages of above 100 square meters. 100 square meters could correspond to a domestic garage, but for above such surface, it is requested 90 to 100 minutes resistance to fire. This means that that fire doors, columns, beams, partition walls, penetration gaps, etc., have to resist for such time between 90 and 120 minutes. And for robotic parking, the requirements are much higher, from 120 to 180 minutes resistance to fire. Regarding reaction to fire, which means whatever you may have on a wall, cable trays, for example, have to be class B. S1 is 0. Class B means the heat release, the quantity of heat. Class B is, first class is A, second B. S1 calls for low smoke, and D0, zero dripping, no dripping. And in the particular case of cables in garages, should meet this standard with an additional parameter, which is the acidity. A1 means low acidity in the smoke. There are other requirements like ventilation, which is very important, not only for the air renovation, but as well for the smoke evacuation, to take out the smoke in a fire case. And all these regulations are based on securing evacuation, geometry of spaces, and the most important thing, the fire load expected in a garage, which is based today in internal combustion engines vehicles. Next. But when we look to the fire load and we look to such batteries of, this is a battery that can have 400 liters and a lot of electrolytes, organic electrolytes, flammable inside them, means that in terms of energy, we are not far from the actual fuel tanks of normal cars. Next. One indication to compare flammability of such solvents is the flash point. So the easiness of ignition could be related to flash point. And when we compare the organic electrolytes in batteries, we see very quite low flash points for certain electrolytes. And when we compare with normal fuels, with diesel or gasoline, which is in the range of 50 degrees centigrade, the flash point. The others, we have some which are really much more flammable and some others a little bit less. So, but as an average, it's similar order of magnitude. Next. Next, please. All right. And here in this case, when we compare vehicle ranges, sorry, the former one, not yet finished. All right. When we compare the range of vehicle, range means how long can you drive a vehicle, which is correlated with the size of your fuel tanks or the size of your batteries. We find out that for similar ranges, low ranges, for example, 400 kilometers, we have a much higher energy release in electric cars than in gasoline cars. So the difference between from 1 gigajoules to maybe 2.5 gigajoules in the electric batteries. However, in the long range, so for big size cells or big fuels tanks, it almost equals. So next. This is a real test on the heat release, energy heat release, and heat release rate, and we can see the evolution is quite similar in this comparison with the electric cars and some combustion cars here on the right side. So next. There are many other things around the electrical vehicles, as has been discussed before, like the chargers, converters, etc. And specifically, there is a recommended, and I'm not sure if it is full regulated, but recommended. This is a standard for the Type 2 official European connector. And among many tests, more than 20 parameters within this standard, there's only one talking, which is the glow wire test, very known. And regarding garages, it is repeated again, the same classification I said before, which is used in the construction codes. So next. Ventilation, that's an important issue, as said before. And the actual regulation really only look for opacity. So they try to reduce the opacity in order to allow evacuation and allow to operate to extinguish the fires. But there is no consideration on the toxicity of the fumes, and with the immobility we are expecting much and more toxic smoke. Next. For example, the hydrofluoric acid has already been mentioned before, is one of the key emissions in this diesel in the cars. So when we compare the diesel car with an electric car, the quantity of hydrogen fluoride is almost double. Next. There are many ongoing projects regarding the study of toxicity from electric vehicles, from toxicity for combustion gases from electric vehicles. This is one of them. There are many others because there is not much knowledge, but hopefully in the coming years we'll have much more information on that, and the electrolytes and the selection of materials for those batteries will be more focused on less toxic materials. Next. Light materials in electric vehicles, this is obviously the tendency is to have a lightweight, either for normal vehicles and as well for electric vehicles, even with much intensity. Those materials has been expressed and discussed before with David Key. But there are other pieces like the front, the back, etc., around the cars, which tends to be more plastic. And here I just would like to outline that many of them are reinforced materials, either with glass, carbon reinforced materials, which under the fire event, they release toxic fumes, but not only toxic fumes, but fibers, and especially nanoparticles in fibers, which are really dangerous. Next. So to conclude, even in those closed areas like garages, it is the worst and most probable fire scenario, and resistance and reaction to fire of all these elements is quite well regulated, as we have seen before. However, there should be is a certain need, because we have really higher fire load with electric vehicles. Such a higher fire load may suggest future revisions of the standards and regulations on reaction resistance to fire in garages. The smoke emission is the issue. It's mainly because of toxicity, and the need for ventilation has to be much safer and should go beyond the actual standards. And regarding active fire protection as well, this is another topic because extinguishing systems is not yet clear what is the best. Obviously, water is not, but there are some foams that work, some others doesn't work, and is still under evaluation. So it's something important. and at the end, need of more research regarding the fireman exposure, because at the end of the day, they are those who are in front of the fire and needs to operate in safe conditions. So with that to conclude, that's the end. Thanks very much. If you have any questions, we can talk later or send me the request.
Okay, muchas gracias. Thanks very much, Vincent.
Thank you.
Okay, let's then move rapidly on to Laurent Tribu. Bonjour, welcome.
Yes, hello.
Hello, over to you. And again, we come to say the industrial view on this. Vincent presented the regulatory side and say the problem statement. And here Laurent is going to present also risks, but also what is currently state of the art in the industry. So over to you, Laurent.
Okay, ladies and gentlemen, good morning. First of all, I would like to thank the organizer of the European Fire Safety Week and PINFA for giving me the opportunity to share with you this short presentation dedicated to fire and overheating risk of electrical vehicle charging station. My presentation will introduce briefly the intrinsic risk of charging station. Then I will detail the different charging mode and their protection levels. And after that, I will list the standard dedicated to charging equipment and the related flammability and thermal resistance requirement in both the IEC and UL bodies. And finally, I will conclude by showing difference between IEC and UL fire protection vision. So next slide, please. Thank you. For charging station installed in outdoor application, in fact, three main risks need to be considered. Due to the high power supply, which can be higher than 20 kilowatts and last several hours for the full charging of electrical vehicle, a risk of overheating may appear, and this implies to use component and material with a high thermal rating. Second risk, the charging station being used by multiple customers and being potentially subject of vandalism. Component degradation could lead to insulation failure and a risk of electrocution for users and inflammation of neighboring substance like fuel, gasoline. And this grounding issue can be mitigated using a Type B residual circuit current device, and which can prevent dangerous leakage current. And the third risk is linked with the overload of the battery, which may happen in case of surge and bad load power transfer limitation. And it is the reason why communication and monitoring devices are added on the majority of high power charging stations. For the charging station installed in indoor parking, the fire load can be significant because each car requires one charging station, and distanciation and ventilation need then to be adapted for this specific infrastructure, as previously mentioned by Vincent. And finally, the flame spread should be avoided in this confined area, and then non-flame propagating cable, but also cable management system are preferred for this application. So next slide, please. So as you probably know, 4 different charging modes are standardized in countries covered by the IEC standard. It's just 3 charging modes in US. The first mode is less powerful as it is limited to 3.7 kilowatts, but it is also the most risky because no specific protection is added to your domestic installation. The second mode is a little bit safer because it implies a communication and charging monitoring device. And Schneider Electric portfolio, it corresponds to the smart wallbox range. The third mode is the most powerful in alternative current, and it requires dedicated power sockets and cable in addition to the charging monitoring. And this mode is addressed by Schneider under the parking EV-Link AC range. And the last mode, which is the fast charging, which operates in DC, and it's very important because the behavior of plastic material under DC and EC can be significantly different. It's at very high power, exceeding 20 kilowatts and sometimes even 50 kilowatts. And the main advantage of this mode is the full charging of the battery in less than 2 hours. In comparison with mode 3, it takes a shorter time, and for mode 2 and mode 1, it was almost 8 hours or even a night. So next slide, please. So in order to ensure the safety of both charging station and plug-in sockets, several standards have been created during the last decades. There are also general standards at the installation level, as you can see on the top. And this installation level are covering the risk of short circuits, overload, electrical shock, and overvoltage through the specification of components to be included in the low voltage switchboard, which is connected to the charging station. So sorry, it was on the next slide. Yeah. So as you can see on this slide, yes, the mother standard is dealing with all the installation and not just the charging station. So and the short circuit and overload are yes, the short circuit and overload, electrical shocks and overvoltage are specified in this mother standard. Next slide, please. Yeah. So if we enter now into the details of the IEC standard and focusing mainly on the flammability and overrating related requirements, we can see that two tests are specified in this standard. The glow wire test for the flammability assessment and the ball pressure for the thermal resistance. The requirements are more stringent for parts in contact with live parts like socket than for the enclosure. So the enclosure should sustain 650 degrees C for the glow wire test, while some components of the plug-in socket should endure 850 degrees C. Regarding the ball pressure tests, the rating differs also for the part carrying live part and the others. When parts are carrying live parts, they should have a minimum ball pressure temperature of 125 degrees C instead of 80 for the other part. And it can be noticed that an additional test of 1 hour at 110 degrees C is specified for the plug-in sockets to ensure that no visible degradation can happen and no flowing of the sealing compounds appear. So we can see that the target of all these tests are mainly to avoid the ignition of a fire induced by the charging station. Next slide, please. The situation in US is different, as the flammability test aims at avoiding the fire propagation from internal and external sources. The US standards integrate 3 tests with a real flame of different energy. So the UL94 is requested for both the enclosure and plug-in and coupler, but the enclosure should pass the highest rating of UL94 of 5V classification. So for people who are not familiar with the 5V test, so 5V test consists in the application of a burner 10 times more powerful than the usual burner for V0, V1, and V2 rating. And moreover, the flame is applied 5 times instead of 2, and the combustion should stop before 60 seconds without flaming droplets. So this rating can be achieved only with flame-retarded polymer, and consequently, the enclosure developed for the IEC compliance cannot be directly used for the US market. In the UL 2202, an additional test is required if the enclosure exceeds 1.83 meter or 0.93 meter square. And this test can be either the Steiner tunnel, which is in the middle of the slide, or the radiant panel, but in both cases, a flame spread rating lower than 200 is specified. And for plug-in socket, the requirements are less stringent, and UL94 rating is at the minimum HB in association with a high arc or wire ignition rating. However, if the HB material are used in this product, in these plug-in sockets, Canada is asking to add a special marking on the product. So we can imagine that the supplier of this product are not using HB material. And the thermal endurance of this product is assessed through a relative thermal index value, which should be more than 100 degrees C. Next slide, please. So to conclude my presentation, we have seen that several standards apply on the EV charging station and plug-in sockets to ensure safety of user, but also safety in the infrastructure. The IEC and UL requirements are different, but each of them constitute an ecosystem with the installation requirement, product standard, and horizontal standard, which has proven to be safe. And the concept of flammability is different in Europe and USA, as the fire ignition from the charging station is addressed in Europe, while it is more the flame propagation from internal or external sources, which is mitigated in US. And finally, the IEC requirement is a little bit less, and it can give the opportunity to introduce recycled material in the application, which could be good for circular economy point of view. So thank you very much for your attention, and I will be happy to answer your question.
Okay, thanks very much, Laurent. Excellent, very good. I've seen some questions in the chat popping up already. We will hopefully come back to them later, unless they can be answered also directly in the chat if it's just a quick question. So let's move on to the next presentation. Risks of electric vehicles from a firefighter perspective, and that already was alluded to in an earlier question about the safety switch in the cars. So I'd like to hand over to Dieter Brands from the Hulpverleningszone Ost, if that was the right pronunciation. So Dieter, over to you.
Good. Thank you very much, and thank you very much for the invitation. Good morning to everybody there, especially my colleagues from all over the world. I saw a colleague from Spain, so he's still quite well. Also, congratulations with the excellent organization. Last but not least, of course, all the speakers for dealing their knowledge with us to improve the fire safety. I was invited to tell something about the risks of electrical vehicles from a firefighter perspective. And to be honest, I'm a little bit concerned about the energy transition that's going on for this moment. Next slide, please. So I will talk a little bit about the risks, our incident response, something about the law, the prevention measures, and the future. Next slide. So as I already told to you, I'm a little bit, and I think a lot of colleagues are a little bit concerned about the energy transition, because which are the problems we have to deal with for the moment. We know that companies are driven or obliged by the government to change their fleet to electrical vehicles. And when they use electrical vehicles, they have to install charging devices. And then they call the fire department and they ask, we want to place in our underground car park, we want to place charging devices. First question, is that allowed? Second question, are there any precaution measures we have to take? And then mostly it stays very still on the other side of the telephone line because we have no rules for this moment. Next slide. The other speakers already told enough about the toxicity of the batteries, the hydrogen fluoride, about the thermal risks, about the high voltage. I already saw this picture presented by the former speaker, but it's a very important one because it shows that the heat release rate between an electrical vehicle and a vehicle with an internal combustion engine is nearly the same. So there is no problem for the firefighters. Next slide, please. When I search a little bit legislation in Belgium, we have no specific rules for the parking of electrical vehicles in underground car parks. We have a nice document that goes about guidelines for car parks, but where we have no any measures for or specific rules for these electric vehicles. There is a little bit that will be published in the electric law. We have a new electric law, and there will be some articles published, but it will be go about the electrical safety. And then last but not least, the fire departments. We are used to deal with difficult problems, and we always try to find a solution. So a few weeks ago, we started some working groups here in Belgium with some representatives of the Ministry of Internal Affairs, the industry and the fire departments to think about this problem. And the key question is which extra precaution measures we should take. Next slide, please. Is there any other legislation? Next slide, please. I found just one document. It's a document from France that gives some rules if you charge electric vehicles in underground car parks. Next slide. I also found an electrical standard, the one who spoke, the former speaker, that deals with the charging of the vehicles. Next slide. And then I also found a very interesting document from our colleagues from the Dutch EIV Institute, where they investigated the fire safety of electrical vehicles in underground car parks. Next slide. So what I want to explain to you now is how will we deal with this kind of incidents on this moment. You see here a nice slide of the fire in the Norwegian car park. It was on the 7th of January 2020. And in the beginning, you could read in the papers that the cause of the fire was an electrical vehicle. Afterwards, I read in the paper that it was not caused by an electrical vehicle, but in an Opel Zafira diesel car. But this is how people will see a real fire, and they will call the fire service. Next. And then we would be very happy if there is inside that car park an automatic fire detection system, so that our fire crews come on the scene when the fire development is still manageable by the fire crews, because on this moment they're also placing these electrical vehicles and charging devices in old car parks without any prevention measures. Next slide, please. It would be also useful if this automatic fire detection system would cut off the power of the charging systems inside the underground car park. Next slide, please. Next slide.
Oops. Looks like we lost the slides.
Yes,
yeah?
sorry everyone. I'm back. I'm gonna share the slide again.
Okay, so I already explained it would be nice if this automatic fire detection would cut off the power from the charging system of these electrical vehicles. Next slide, please. We arrive at the scene. After a few minutes, we will be at the car park. Next slide, please. And then would it be very good if our firemen knew that there are electrical vehicles inside that car park. So it's very important that there is the signalization that we know that there are electrical vehicles in the car park. Next slide. You see on the right a manual switch. So normally we could ask this this device to cut off the electricity power from the charging devices inside that car park, so that we are sure that when the firemen enter the underground car park, there's no electricity anymore in that underground car park. Next slide. And then we prepare ourselves. You see on the right graph, you see two hoses of 45 millimeters, which give us the capacity to extinguish a fire between 10 and 15 megawatt. A car that burns without too much plastic has a power of 5 megawatt. So one or two cars in fire, we can manage this with the equipment that you see there on the right graph. Next slide. And then we enter the car park using the slope. Next slide. And then because there is a lot of smoke inside the car park, because the ceiling height is very low, there is less entrainment in the smoke. The smoke is very hot, very thick, and very black. So we use on the right graph our thermal cameras. Next slide. And then the fire is extinguished. And then we hope that there is a little ventilation opening inside that car park, so that we can use our overpressure ventilators to put out all the toxic smoke. Every speaker already talked about the hydrogen fluoride, which is very dangerous for the firefighters. So we should have a little opening to push all these toxic smokes outside the car park. Next slide. And then we change a little bit our policy in comparison with a normal diesel car, because when we have extinguished a diesel car, it can stay inside the car park. But when it's an electric vehicle, we know already that the battery will reignite. So we have to get the car out of the car park. So I think it's very important to make the good arrangement with the towing service. I did the same here in Leuven, and they ensured me that they could, even from any position or damage, they could always get the car out of the car park if it has at least a ceiling height of 1.85 meters. On the right graph, you see the special equipment that they will use. But again, this is a very big difference with a traditional car. We have to put it always out of the car park. Next slide. And then, of course, we will wash the car. Yeah? We will put the car in a water containment to stop the process, and we will leave it there until the process stopped. Next slide. And then, of course, we have to remove the contained water with toxic substances. So we have to contact a specialized firm to remove all the contaminated water. Next slide. I have a big question. How will we do that if there is a bus who got on fire? They asked me a few weeks ago, a bus company, we will drive electric buses here, but we have 2 batteries on top of each 1 ton. So what in case of a fire? I said, we have no water containment where we can put that bus in. So this is a big problem. Next slide. You see here the fireman standing on the roof of the bus, trying to extinguish the battery, but I think it's not a good way to put a fire out, knowing that there is a lot of toxic smoke in the neighborhood. Next slide. So my general conclusions are, very shortly, there is no higher fire load when it's an electric vehicle. We know that there's always a reignition possible. The release of a lot of toxic smoke. The fire spread, I don't know if an electric car will give faster fire propagation to another car. And then I put some measures on the paper, like at least a minimum fire detection, the protection of the fast charging devices against the mechanical impact, an automatic shutdown of the electric charging stations in case of fire, a manual electric switch at the entrance, sprinklers, is it necessary or not? I don't know on this moment. And of course, adequate extinguishing media. Next slide. So my conclusions for the future are, I think it's very important for the fire departments that we have a uniform and multidisciplinary fire law. Mostly the fire laws are driven by changes in other laws after a few incidents. So I think the fire service should be involved in any regulatory framework. There is more investigation and testing necessary. Then another question, how should we deal with other small lithium-ion batteries? I give an example. If you have tomorrow an incident in your home and the battery is become a little bit bigger, yeah, what are you going to do with it? So we have here trying to make an appointment with a recycling firm to place containers in our area where we can put these batteries and they can be collected afterwards by this firm. Next slide. These are my resources. So if everybody's interested to read something more, you can find it in all these texts. And that's all, folks. Thank you very much.
Thanks very much, Dieter. Very nice overview of the challenges and presentation of the challenges you're facing. Looking at the time, it looks like we will overrun a few minutes only. So if people can stick around, we are not bound to shut down the line at 12:30 sharp. So anyone who can extend or stay around a few minutes longer, you're most welcome to do so, and we'll keep the line open, or we will continue. So just as a warning. Or announcement, but now quickly handing over to Lars for our last presentation of today, and along the lines of what we just heard from Dieter, the challenges of fires from electric vehicles underground and in tunnels. Over to you, Lars.
Thank you very much. You see